8 inches per mile squared. Now, it is interesting how this one is used. Flat earthers will use this one all the time to determine how much of some object should be hidden due to the curve of the earth. Sensible people will regularly jump on this not being the correct equation to describe curvature, as this describes a parabolic system. Firstly, this is an approximation that holds quite well at short distances, but it does not account for observer height. That is to say that this approximation only holds if you are considering short distances and eye level is at the ground, as in you are buried in the ground up to halfway across the iris of your eye. What this expression is used for is as a rule of thumb for back-of-the-envelope calculations in civil engineering and surveying. But to what extent is it a reasonable approximation? Also, as a fun bit, what is curvature exactly? Well, in short, curvature is just a number which describes how, well, curvy a line is, and it is given by the inverse of the radius of curvature at a given point on the line. What the expression describes is as follows. Take your position on the Earth and take a flat plane which is tangent to the Earth at that position. The distance between the Earth's surface and the tangent plane is then given by the square of the distance along the tangent plane in miles, multiplied by 8 inches. Where does this actually come from? Well, this comes from a great number of approximations. Firstly, we take the tangent plane to be at the top of the Earth. As you travel some distance along the top of the tangent plane, you change your angular separation from the original position. The angular separation is related to the distance by the expression distance is equal to the product of the radius of Earth and the sine of the angular separation. The drop distance is given by the difference between the radius and the cosine of the angular separation times the radius. Here we bring in two approximations. The first is the small angle approximation where sine of theta is approximately equal to theta. The second is that we take the first two terms in the series expansion of cosine of theta, which is cosine of theta is approximately equal to 1 minus theta squared over 2. So our expression for drop height then becomes this. From our small angle approximation, we know that if d is equal to r sine theta, d is also approximately equal to theta r. And we can rearrange for theta. And we can stick that into our expression for drop height, whilst being careful to note that d is distance. I'm not fucking up the second derivative. Remember how I said that the inverse of the radius is curvature? Well, this becomes this expression then. If you take your distances in miles, then k over 2 is approximately 8 reciprocal inches. Yes, flat earthers, units are important. The question becomes, how well does this approximation actually hold? Because we can also do it without the approximation. The distance along the tangent is then just taken as r sine theta, so theta becomes this expression, and our expression for drop height becomes this. We could simplify this, but I can't be bothered. We can then also plot the functions and the difference between the two of them. So we see that the difference between these functions isn't too bad at short distances, and the approximation is pretty decent, provided that you are using the approximation for its actual intended use. If you are using it for figuring out whether you should be able to see the top of a mountain while standing on top of another, this thing is no use, and it should never be used to determine how much of an object should be obscured.